In this video, we're going to look at determining the initial concentration of a weak base if we know the pH of that solution. So a typical question you might see is, a solution of sodium acetate has a pH of 9.2. What is the concentration of the solution? So the first thing we want to do is we want to write our equilibrium expression. Now, sodium acetate is an ionic compound, so NaCH3COO. This is going to dissociate in solution, and the base that we care about is CH3COO minus. Okay, so that's what we're going to use for our ice table. So acetate, aqueous, reacts with water, and because it's a base, it's going to accept a proton from water, forming acetic acid, aqueous, and hydroxide. Okay, now we're going to quickly, at the beginning of this, look up the Ka of acetic acid, of its conjugate acid. And the Ka is 1.8 times 10 to the negative 5. So we're going to need that for our calculation. We're going to set up our ice table, ICE, and as usual, we're going to just ignore that water exists. So we don't know the initial concentration of CH3COOH, COO, so we're going to set that as X. We know that we don't have any acetic acid or hydroxide to start. Now this is a lot of unknowns in our table, but we're actually going to be able to solve for the equilibrium concentration of both acetic acid and of hydroxide using our pH. Okay, so we know that these two are equal. If we ionize one molecule of acetate, we produce one molecule of acetic acid and one molecule of hydroxide. So the concentration here is equal to the concentration here. And so if we have our pH as 9.2, we can find pOH by subtracting that from 14. And that's going to equal 4.80. Okay, that's going to allow us to determine the concentration of hydroxide. So hydroxide equals 10 to the negative pOH. So it's going to be 10 to the negative 4.80. And we get 1.6, so 1.58, but we'll round to 1.6 times 10 to the negative 5 molar. So that's going to be our equilibrium concentration of both acetic acid and of hydroxide. So we can input that into both of these slots. Because we started with the 0 moles per liter for both of those, that's also going to be our change. So plus 1.6 times 10 to the negative 5. And it will be the change for our acetate, but just negative. So our acetate concentration at equilibrium is going to be X minus 1.6 times 10 to the negative 5. And we can solve for this using our Kb expression. So Kb is the product of our products. So acetic acid times hydroxide divided by our reactant, so in this case acetate. We need to solve for Kb, and we're going to use the Ka value of its conjugate acid, so of acetic acid, so Kw over Ka, and we get 5.6 times 10 to the negative 10. So we can plug that number in. 5.6 times 10 to the negative 10 equals 1.6 times 10 to the negative 5 squared over x minus 1.6 times 10 to the negative 5. We're not going to use the approximation method here because we can actually solve for x directly without having to use a quadratic formula. So we're going to quickly rearrange this equation, and I'm just going to write the rearranged state. So this is going to be 5.6 times 10 to the negative 10x minus 8.9, so I'm just going to round to 8.9 times 10 to the minus 15. Oopsies. So that's the 5.6 times 10 to the negative 10. times 1.6 times 10 to the negative 5. And then this is going to equal 2.56 times 10 to the negative 10. So we can rearrange this for x, and we get 0.46 molar. And that's the initial concentration of our solution.